In the last week lecture session, we had discussed about the load line analysis. For today's lecture session, we will discuss about rectifier and clipper. Along our lecture session, there will be some exercises and a bit discussion about our lecture contents. Hopefully, all the students will listen and watch this video carefully as to understand the flow of my explanation. Okay. Same within our previous lecture session, there will be several parts of this lecture video where the students require to answer several quiz questions based on this lecture video, and this quizzes basically will be as the lecture session's attendance. Okay, right, let us begin the lecture. Firstly, I will start with listing down the learning outcome here for Chapter 4. For this lecture session, there are 2 outcomes to be covered and achieved at the end of the lecture session by all the students. Today all the students are expected to explain the process of rectification by using half-wave and full-wave rectifier. At the same time, the ability of analyzing the output voltage of clipper and clamper will be our priority for today's outcome. However, maybe for today, I cannot finish all the lecture. The part 5 for this chapter will be continued on next week. In this part 4 of chapter 4, we will discuss about rectifier. Here, I will explain about the types of rectifier. We will discuss 2 types, which are half-wave and full-wave rectifier. Later, the concept of clipper also will be exposed as the introduction of the sub-chapter 4.5.4. Rectifier. Have you heard about rectifier before? If yes, then good. Else, we will discuss it today. Do not worry. Rectifier is an electrical device that converts alternating current to direct current. Or we say this way as converting AC to DC. This conversion process is also called as rectification since it straightens the direction of current. Why the rectifier is important? Rectifiers are usually been used as a component of direct current supplies and high voltage direct current power transmission. As noted, detectors of radio signals serve as rectifiers. In gas heating systems, flame rectification is used to detect presence of a flame. As several examples given in the last slide, rectifiers are important for applications such as radio, television, computer, or any other electronic equipment which require a steady constant direct current, which similarly produced by a battery. In general, we can say that the output of rectifier is in brackets smoothed by an electronic filter to produce steady DC current. For this lecture session, we will consider there are 2 types of rectifier. There are half-wave and full-wave rectifier. The first is half-wave rectifier. Before we discuss about these 2, I will be using an input on the left and output on the right side of the slide. From the previous slide, we did hear about converting alternating to direct current, right? As alternating current is concerned, the input side can be described as up and down of voltage as sine wave as on the left. A normal sine wave has a period of t for one cycle. As a sine wave, this input Vi is divided into two R, positive and negative. A sine wave also can be described as Vm as amplitude or maximum in Vi multiply with sine function of angular frequency with t time. The right side here is the half-wave rectifier, which has diode connected with a resistor. Since the sine wave has positive and negative of voltage input Vi, here we can describe it as two regions of conductivity. Conduction region is stated when t from 0 to t by 2. As the diode is connected to the positive Vi as in figure on the left, it will be in forward biased mode. Here, the diode will be acting a closed switch as in the middle figure here. This diode will let the positive pulse of sine wave to appear across the load resistor. So, the output VO in the right figure for t0 to t by 2 is only for this positive pulse of sine wave. This alternating current when t is from t by 2 to t will be the non-conduction region. When the input sine wave goes negative, the diode will be in reverse biased mode. The polarity of the input Vi is as shown in left-hand side figure, and the resulting polarity across the ideal diode produces an off state with an open circuit equivalent. At this condition, no current flow in the circuit. Then, we can explain this as an absence of a path for charge to flow, and VO equal IR as in Ohm's law. This will be 0 multiply R equals 0 volt for the period t by 2 to t. No negative voltage appears across the load resistor. So, the output voltage will be 0 during the negative cycle as in figure on the right. The input Vi on top and the output VO at the bottom are sketched together here for comparison purposes. Here is the half-wave rectified signal without silicon diode effect. The output signal VO now has a net positive area above the axis over a full period and an average value determined by VDC equal to 0.318 Vm, where Vm is the peak of voltage. The process of removing 1/2 the input signal to establish a DC level is called half-wave rectification. Now, half-wave rectified signal with silicon diode effect. The effect of using a silicon diode with Vk is 0.7 volts is demonstrated in figure on the most left for the forward bias region. The applied signal must now be at least 0.7 volts before the diode can turn on. For levels of Vi less than 0.7 V, the diode is still in an open circuit state and VO is 0 volt, as shown in the same figure. When conducting, the difference between VO and Vi is a fixed level of Vk is 0.7 volts and VO is Vi minus Vk, as shown in the figure on the most right. The net effect is a reduction in area above the axis, which reduces the resulting DC voltage level. For situations where Vm larger than Vk, the following equation can be applied to determine the average value with a relatively high level of accuracy. VDC is approximately equal to 0.318 of the difference between Vm and Vk. This figure shows the difference between ideal and constant drop model. OK, now we will look at example related to half-wave rectifier. Refer to figure 16. Sketch the output voltage and determine the DC level of the output of the circuit. Here, there are two main targets, which are output voltage and DC level of output, right? On the left we understand that Vm in Vi is 20 volts. And the 2 kΩ of resistor is used in the circuit on the right. Careful, here, the polarity of diode and the Vi. Is the diode as the forward biased mode or the other one? OK, let's solve this problem. As the reversed biased mode is concerned here, VDC this time is minus 0.318 by Vm. The negative sign indicates that the polarity of the output is opposite to the defined polarity of figure on the most left. For a silicon diode, the output has the appearance of bottom figure and VDC is approximately minus 0.318 by Vm minus 0.7 volts. We will minus 6.14 volts for the VDC. The DC level obtained from a sinusoidal input can be improved 100% using a process called full-wave rectification. Here, full-wave rectifier is classified into two types, bridge rectifier and center-tapped transformer. The most familiar network for performing such a function appears in top left figure with its 4 diodes in a bridge configuration. During the period t from 0 to t/2, the polarity of the input is as shown in top right figure. The resulting polarities across the ideal diodes are also shown here to reveal that D2 and D3 are conducting, whereas D1 and D4 are in the off state. The net result is the configuration of figure at the bottom, with its indicated current and polarity across R. Since the diodes are ideal, the load voltage is VO is equal to Vi. For the negative region of the input, the conducting diodes are D1 and D4, resulting in the configuration of Fig 2.56. The important result is that the polarity across the load resistor R is the same as in top right figure at page 15. Establishing a second positive pulse in the rightest bottom figure. Over one full cycle, the input and output voltages will appear as shown in this figure for the full wave rectified signal without silicon diode effect. Since the area above the axis for one full cycle is now twice that obtained for a half-wave system, the DC level has also been doubled and VDC is double of normal half-wave rectifier VO as 0.636 volts. When the full-wave rectification with silicon diode effect, VDC is approximately equal to 0.636 by Vm subtract to 2 Vk. OK, now we will look at example related to full-wave rectifier. Example 10. Determine the output waveform for the bridge circuit as shown in Figure 17 and calculate the output DC level. Point 1. Solution for this example 10. The network appears as shown in topmost left figure for the positive region of the input voltage. Here, for the positive cycle, redrawing the network results in the configuration of top second from the right figure, where VO is half of VI, or we can say VO max equals 1 by 2 VI max equals 1/2. 10 volts is 5 volts. For the negative part of the input, the roles of the diodes are interchanged, and VO appears as shown in bottom figure. The effect of removing two diodes from the bridge configuration is therefore to reduce the available DC level to the following. VDC is 0.636 by 5 volts equal to 3.18 volts. For tutorial question 1, sketch the VO waveform for the circuit shown in Figure 7.7 and determine the DC voltage available. Firstly, we need to sketch the VO from Figure 7.7. By considering the point C as the node, we can redraw this circuit. From the idea of full wave rectifier at the pulse half cycle. After that, we can solve the VO and the VDC. For tutorial question 2, sketch VO for the network of Fig 2.174 and determine the DC voltage available. A second popular full-wave rectifier appears in left figure with only two diodes but requiring a center-tapped CT transformer to establish the input signal across each section of the secondary of the transformer. During the positive portion of VI applied to the primary of the transformer, the network will appear as shown in right figure with a positive pulse across each section of the secondary coil. D1 assumes the short circuit equivalent and D2 the open circuit equivalent, as determined by the secondary voltages and the resulting current directions. The output voltage appears as shown in the figure. During the negative portion of the input, the network appears in left figure, reversing the roles of the diodes but maintaining the same polarity for the voltage across the load resistor R. The net effect is the same output as that appearing in figure on the right with the same DC levels. D2 assumes the short circuit equivalent and D1 the open circuit equivalent, as determined by the secondary voltages and the resulting current directions. This will be the summary of all types of rectifier. Now we will discuss clipper. Clippers are the circuit that use diode to clip away a portion of an input signal without distorting the remaining part of waveform. The use of clipper is to limiting circuits with a specific voltage by limiting the positive or negative amount of an input voltage to a specific value. Here is one basic example of the clipper. This top area of positive pulse in sine wave was cut by the clipper. There are two general categories of clippers: series and parallel. The series configuration is defined as one where the diode is in series with the load, whereas the parallel variety has the diode in a branch parallel to the load. The response of the series configuration of second most left figure to a variety of alternating waveforms is provided in the three most right figure. Although first introduced as a half-wave rectifier, for sinusoidal waveforms, there are no boundaries on the type of signals that can be applied to a clipper. In this figure, for instance, any positive voltage of the supply will try to turn the diode on. By establishing a conventional current through the diode that matches the arrow in the diode symbol. However, the added DC supply V will oppose that applied voltage and try to keep the diode in the off state. The result is that any supply voltage greater than V volts will turn the diode on and conduction can be established through the load resistor. Keep in mind that we are dealing with an ideal diode for the moment, so the turn-on voltage is simply 0 V. In general, therefore, for the network of this figure we can conclude that the diode will be on for any voltage Vi that is greater than V volts and off for any lesser voltage. For the off condition, the output would be 0 V due to the lack of current, and for the on condition it would simply be VO equal to Vi minus V as determined by Kirchhoff's voltage law. Example 11. Determine the output waveform for the sinusoidal input of figure 18. The transition model is substituted in figure on the left, and we find that the transition from one state to the other will occur when Vi equal to -5 volts. In middle figure a horizontal line is drawn through the applied voltage at the transition level. For voltages less than -5 V the diode is in the open circuit state and the output is 0 V, as shown in the sketch of VO. Using the similar figure, we find that for conditions when the diode is on and the diode current is established, the output voltage will be the following, as determined using Kirchhoff's voltage law: VO equal to VI plus 5V, where 20 plus 5 is 25 volts. The analysis of clipper networks with square wave inputs is actually easier than with sinusoidal inputs because only two levels must be considered. In other words, the network can be analyzed as if it had two DC level inputs with the resulting VO plotted in the proper time frame. Example 12. Find the output voltage for the circuit in figure 19. For Vi equals 20 volts, T from 0 till T by 2, the network of Fig 2.78 results. The diode is in the short circuit state, and VO equals 20 volts plus 5 volts equals 25 volts. 46 equals minus 10 V. The network of Fig. 2.79 results, placing the diode in the off state, and VO equals IR equals 0 by R is 0 volts. The resulting output voltage appears in Fig. 2.80. With that, I end my lecture for this chapter 4 part 4 about the rectifier and clipper. I hope that you all gained knowledge and ideas this chapter. If you have any question, please contact me at nixarifi@utem.edu.my. I will see you on the next lecture session.
Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.